1.3, manufacturing microprocessors. At this point, you may wonder why we need to learn this much details about manufacturing, transistors, microprocessors. So let me give you the reason. Our textbook does not give this much detail. Yeah. After I taught this course many years, after so many years, I got something pretty common when I talk about computation formulas. In our next part C, I will give you many computation formulas because we want to calculate the manufacturing cost. When we do that, when we derive those formulas, many students ask questions, why we do not do this way or that way? Why many students have such questions? Because they do not have this background. So for that reason, in order to answer questions in the formulas in my next class, part C, I need to give you enough background. Then at that time, now you understand, oh, we need to do it in this way. So this is the right way to do. So that's the reason. Okay? Yeah. All right, so let's continue. This time we need to learn making microprocessors from silicon. Okay? All right. First, types of crystalline silicon. Crystal. Yeah. The crystal, you know, there are some nice properties for crystals. Silicon, this element has some special crystal structure. Regarding the crystalline silicon, there are two main types. The first type, called a monocrystalline. Mono, yeah, single. Mono means single. Yeah. Monocrystalline. All right? Yeah. Another polycrystalline. From the name, you can guess the structure a little bit. Yeah. First, let me show you the picture of monocrystalline silicon. Yeah. Like this. Okay? Yeah. So the shape, like that. Yeah. All right. And then this one, polycrystalline. Compare with this. Can you see the difference? These two. So one shiny, smooth. The other, you can see, you know, the surface not very smooth. Okay? Yeah. Because of their different properties. Yeah. First, let's look at the monocrystalline. Also called a single crystal silicon. Okay? Is the base material for silicon chips used in virtually all electronic equipment today. Yeah. So the most useful type crystalline silicon is this one, monocrystalline silicon. Yeah. All right. Then polycrystalline is a material consisting of multiple small silicon crystals. So the structure, so not uniform structure. The structure contains several different types of crystal structures. Okay? Yeah. So because of those different types of crystal structures, so you can see the shape on the surface. So you see not very smooth, you know. Yeah. Yeah. And given the material, it's typical. Here, metal flake effect. Here, the surface you can see, so that is the metal surface effect. Metal flake effect. Flake, yeah. Snowflake, metal flake. That effect. Because of different structures, different crystal structures to form this type. Yeah. All right. So now, when we make crystalline silicon, this is the better material, right? So you can see monocrystalline silicon, better material. Polycrystalline, not as good as monocrystalline, but they can be used to convert to monocrystalline. So we do not waste it. So we still use polycrystalline silicon, but we need to do some further processing, improvement, manufacturing procedure steps to make it monocrystalline silicon. All right. Okay. Convert it. So still, you need to spend some more money to do the conversion. So that means the cost to get monocrystalline silicon more expensive, because you need to do a lot of things. After you get polycrystalline silicon, you still need to do conversion. Okay? All right. So next, production of monocrystalline silicon. So let's look at the main steps in the production. First, use melting high purity semiconductor grade silicon. Melting. Okay? Look at this shape. So melting silicon, high purity, 99.999, many nines, high purity, melting silicon. So the first step. After that, then a special, very special step. Use a seed to initiate the formation of a continuous single crystal. This step is very special and very important, like this. So here, there's another, picture showing you the details. A seed, okay? High purity silicon rod. Right? You see that rod used as a seed. Here also, that rod, that seed, okay, rotated inside a melting silicon. Okay, so we will see the details more. Then, this method was created by a Polish chemist. His name is this. Zokrasky. So you can see these 5 steps. You can see the detail of Zokrasky method. The first one, look at this picture. The first step, melting of polysilicon doping. See? Polysilicon. First we use polysilicon and we melt it. Okay? Then we do doping. So look at these things. Some special materials to do the doping. So what's the doping here? There is special meaning in semiconductor industry. The doping here, the meaning is the intentional introduction of impurities. Although we want high purity, but for some special reason, people need to add some special materials. So introduction of impurities into the intrinsic semiconductor for the purpose of modulating its electrical, optical, and structural properties. You want to change some properties, special properties. So you add some, special minerals inside. So that's the doping step, the first, all right? Second, introduction of the seed crystal. So now that seed, rod, crystal, high purity raw crystal, okay? Dip into the melting silicon step. All right, so here, dip are precisely oriented, so orientation, special orientation, rod-mounted seed crystal into the molten silicon. Okay, that's the second step. The third step, then beginning of the crystal growth. You want to, make the crystal, monocrystalline silicon grow, attach to the rod, bigger, so make the, rod bigger and bigger. Okay, Then, so you rotate, right? At the same time you rotate, try to grow. At the same time, pulling, slowly pulling up. Okay, so then growing bigger. You can see growing bigger. So this way, growing bigger. Okay, and at the end, formed crystal with a residue of melted silicon. At the end, very big cylinder, thick, big, heavy cylinder was formed. The last step. So let's see. The rod is then slowly pulled upwards and rotated simultaneously, allowing the pulled material to solidify into a monocrystalline cylindrical ingot. So that's the description of that whole procedure. The Krauski method. Because the name hard to pronounce. So sometimes people just use CZ method. Okay? CZ method, first two characters. It's easy to, call it. Krauski method. All right. How big is the final rod or final cylinder? So that's cylinder shape, big cylinder shape. Here, let me give you the number, roughly, up to 2 meters in length, 2 meters, more than 6 feet, 2 meters, okay, and weighing several hundred kilograms. Kilo. 1 kilogram is more than 2 pounds, right? More than 2 pounds. So here, weighing several hundred kilograms, that heavy. So that big, that heavy. Okay? So that's the important step. Monocrystalline silicon step. All right, high purity. Then next move to some more step. Next step, manufacture silicon wafers. Our goal, we want to manufacture microprocessors. CPU, microprocessors, CPU, microchips. That's the goal. So now, we need to do another important step. Manufacture silicon wafers. Here, we need to do many steps on the wafers. Each wafer, so a lot of special treatment steps. Here, I give you this picture, just give you some general idea. We will not go through the details of each step. That's not important for this course. So we will not go that much of depth. Yeah. So you only need to know several important steps still need to be done until we get a final product. Yeah. One of the steps here, I just show you a real picture. Yeah. So doing the processing, something like this. Okay. All right. Then facts of silicon wafers. Yeah. So wafers are formed of highly pure, nearly defect-free single crystalline material. Defect-free. Yeah. The purity extremely high. So you can imagine the cost also very high to make that high percentage purity. Yeah. So with a purity of 9 nines, you can count number of nines, 99.79 after the decimal point. So the total 9 nines. So 9n or higher. So you can imagine how hard to make monocrystalline silicon. Yeah. Although the original material very cheap to get, right, on Earth. People just get from sand. So easy, so cheap. But it does not mean the final product manufacturing cost is low. No, because you need to make extremely high purity. Yeah. That is very expensive. All right. Next, silicon wafers are available in a variety of diameters. How to measure the your technology levels here also reflect important technology evolution from 25.4 millimeters that's 1 inch, 25.4 1 inch, to 300 millimeters. The current technology, 300 millimeters technology, approximately 11.8 inches. So that's the diameter of that ingot. Yeah, we call that ingot. Okay, yeah. But usually people call it 12-inch technology. Yeah, so approximately 12 inches the diameter. So people call it 12-inch technology, the current technology. Yeah. The diameter has gradually increased to improve throughput and reduce cost with the current state-of-the-art fab using 300 millimeters with a proposal to adopt 450 millimeters. Here, let me explain this sentence. First, we know in order to reduce the manufacturing cost, we want to increase the throughput. So that's the output production, right? On one wafer, how many microchips you can cut out, you can produce out of it. Okay? The throughput, the output number, throughput. All right. Then, because you distribute the total cost on as many microchips as possible on the wafer, so you will reduce the average cost for each chip, each CPU, one chip, one CPU. So you get a reduce the cost. So that's very important. So that's why the larger the diameter, the more microchips you can make from one wafer, and supposed to be lower cost. Yeah, the reason I said that's supposed to be because due to some many bottlenecks, so the building cost to build more advanced technology chips, the cost could be higher. Yeah. occasionally. Yeah. Then, with a proposal to adopt 450 millimeters, people also call 18-inch technology. So this one, 12-inch technology, 300 millimeters, 12-inch technology, and proposal. So that means this technology is still not available. Already after many years development, okay, more than 5 years development. So this technology is still far away from it can be used. Yeah. All right. Yeah. You can see, so this shape, yeah, ingot, right? So that ingot, yeah. Also we call it monocrystalline silicon bowl. Monocrystalline silicon bowl. Yeah. So that ingot, yeah, another name of it. So the bowl is then sliced, cut, okay, sliced, yeah, cut, yeah, with a wafer saw, okay, with a wafer saw, okay, saw to cut it, yeah, and polished to form wafers. Then you need to polish it, make a nice, shiny, smooth, shiny, nice shape, yeah, wafer. Yeah. So like this, okay, yeah. After polish, then you can cut microprocessors, microchips out of it. Yeah. So that's the general step. All right. Next, our last slide of this video. So we see the final step. Microprocessor manufacturing process. Yeah. All right. So when we start from silicon ingots to microchips. Okay? Suppose we have already built many silicon ingots. Yeah, like here. So very rough, right? Yeah, many big, long cylinders like that. That's before further processing. So things like that. Yeah. After that, next step. The ingot is then ground, okay? Ground, the surface, outside, the shape, ground into a perfect 200 millimeter or 300 millimeter diameter cylinder, okay? Yeah. With a small flat cut on one side, okay? Yeah. For positioning accuracy and handling. Yeah. So processing like this. After processing, you will get this kind of perfect shape cylinder. Yeah. Very nice. Okay? Yeah. Ready for slicing into the wafers. So next step, we want to get the wafers. Now, each ingot is then cut with a high precision diamond saw, special saw, the diamond, yeah, very hard diamond saw, into more than 1,000 wafers. So one cylinder, one ingot, you can cut more than 1,000 wafers. Yeah. So you can see large number of wafers and a large number of microprocessors, because you want to make the manufacturing cost as low as possible. Yeah. All right. Each wafer is less than 1 millimeter thick. 1 millimeter thick. Very thin. Very thin. Okay? Like the picture here. So each wafer, you can see. Yeah. So then we need to move to the next step. Yeah. So the next step, a special fixture tests. We need to do testing. Okay? Before we do the cutting, we need to do testing. Okay? Tests each of the chips. Yeah. So one small rectangle shape. Each chip has a rectangular shape, but very close to square. Not exact square, very close to square. Okay, yeah. So, yeah. Tests each of the chips on the wafer and marks the better one. Yeah, a special machine. Here, you do testing like this. A special machine will detect if there is any defect. Yeah. Yeah, remember in the previous video, we saw a picture, put a gray dot on a die. So at that time, we use a name called a die, D-I-E. Yeah. Put a mark on it. Yeah. So then later, we will throw away all the bad dies. Yeah, all the bad dies throw away. Yeah. Only keep the good dies. Okay? Yeah. So using this machine to do the testing, initial testing. Yeah. Later we will do more testing. Yeah. Here, this is the first test. Yeah. Then, now cutting. This is the last step. Yeah. After testing, now we do the cutting. Okay. The chips are then cut from the wafer using either a high-powered laser cut, okay, or diamond saw. Also diamond saw can be used to cut. So we get microprocessors. This is one chip, one microprocessor, one CPU, the final product. Yeah. And we put in a PC. This chip, microprocessor, we put in a CPU, we put in a PC, so we can build a computer. So look at this kind of procedure. Yeah. So I try to skip some unnecessary details, but at the same time, I want to show you the important steps. Because in our later discussions, we need this background. Otherwise, we will have a lot of questions. All right, so now I think we are ready for the next round computation. Yeah. All right, so let me stop here. Yeah.